Hello students, our next topic is on the Meson theory of nuclear forces. This explains the particle exchange. This is the particle exchange which can produce either attraction or repulsion. The nuclear forces are explained on the basis of particle exchange. We know that in a molecule, the atoms are held together by the exchange of some particles. That is, when electrons are exchanged, you get an ionic bond or a covalent bond, etc. Like that, by the exchange of such particles, the atoms are held together. A similar approach is there operating between the nucleus. That is what is called the particle exchange in the case of nuclear forces. This is the Meson theory of nuclear forces, which explains the particle exchange which can produce either attraction or repulsion. The Japanese physicist Yukawa was successful with this theory in 1935, proposed that particles intermediate in mass between electrons and nucleons are responsible for nuclear forces. Okay, particles having a mass between electrons and nucleons are responsible for nuclear forces. Today, these particles are called pions. They may be charged, pions may be charged, so it is represented as pi plus or pi minus, or there are neutral pions also, pi 0. Okay, this is lately discovered, and these are the members of a class of elementary particles collectively called mesons. So elementary particles are of different types, and among which these pions come under the category of mesons. The word pion is a contraction of the original name pi meson. This pi meson is named as pion, right? Now, according to Yukawa's theory, every nucleon continuously emits and reabsorbs pions. Every nucleon continuously emits and reabsorbs pion. If another nucleon is nearby, an emitted pion may shift across to it instead of returning to its parent nucleus. So, it can either come back to its parent nucleus or go to another nucleon nearby. So the associated transfer of momentum is equivalent to the action of a force. Okay. Now the nuclear forces are repulsive at very short range as well as being attractive at greater nucleon distances. Otherwise the nucleons in a nucleus would mesh up. Okay. These two points are to be explained on the basis of this theory. Okay, nuclear forces are repulsive at very short range and attractive at nucleon distances. Okay, this has to be explained in Yukawa's theory by this Meson theory. So that particle exchange can be explained by a simple picture. Let us imagine two boys exchanging basketballs. Okay, these are the two figures. If they throw the balls to each other, what will happen? The boys move backward, right? And when they catch the balls thrown at them, their backward momentum increases. Okay, so when they are throwing the balls to each other, there is a backward momentum due to this throw, as well as when they catch up the balls thrown to them. Okay, then their backward momentum increases. So their movement of the nucleon is towards backwards. So the repulsive force due to the particle exchange is explained this way. Okay, this method of exchanging basketballs has the same effect as the repulsive force between the boys. Now if the boys snatch the basketballs from each other's hand, this picture. However, the result will be an equivalent to an attractive force acting between them. So if they try to snatch the ball between them, the reaction forces towards each other. So there is an attractive force. So such a case occurs in the case of particle exchange. Now there is a fundamental problem present itself at this point. If the nucleons constantly emit and absorb pions, why are neutrons and protons never found with other than their usual masses? Since pion has a mass, we never discover a neutron or proton with less mass. This answer is based upon the uncertainty principle. So the uncertainty principle says that delta E delta T is greater than or equal to H cross by 2. So this change in energy into change in time, the time difference, time interval, should not be less than. It should be always greater than or equal to H cross by 2. That is, an event in which an amount of energy delta E is not conserved is not prohibited. It is not prohibited so long as the duration of the event does not exceed H cross by 2 delta E. Okay. So if the duration of the time does not exceed this much, this delta E change in amount, in energy change is not prohibited. This condition lets us estimate the pion mass also. Now let us assume that a pion travels between nucleons at a speed of approximately c. V approximately equal to c, but actually V is less than c. That the emission of a pion of mass m pi represents the temporary energy discrepancy. Okay, so delta E is equal to, by the emission of pion, the change in energy is approximately m pi c square, and that delta E into delta T is approximately h cross. Okay, now the nuclear forces has a maximum range of distance 1.7 Fermi, and the time delta T needed for the pion to travel this distance is delta T is equal to the distance r, it is 1.7 Fermi, by the velocity of the particle. So it is r by, approximately it is r by c. Okay, this is the time taken by the pion to travel the maximum distance, maximum range of the nuclear force. So it takes this much time, r by c time. Okay. So we therefore have delta E delta T is approximately h cross or m pi c square. It is the discrepancy in mass, energy, and delta T is r by c. Therefore m pi, mass of pion is h cross by rc. When we evaluate this, you get the value as 2 into 10 raised to minus 28 kilogram. This figure is about 220 times the rest mass energy of electron. This is lately discovered after the proposal. There are some reasons behind them of their belated discovery. So the uncertainty principle permits the creation, transfer and the disappearance of a pion to occur without violating the conservation of energy, provided that the sequence takes place fast enough, right? Here a positive pion emitted by a proton is absorbed by a neutron. As a result, proton becomes a neutron and the neutron becomes a proton. Okay, here initially it is a proton and here it is a neutron at a distance r, which is 1.7 Fermi. This is the maximum nuclear range. So if this proton emits a pion pi plus, okay, pion with a speed c, and this proton now becomes a neutron. Now for this pion to travel this much distance, it takes a time t equal to r by c. At time t equal to r by c is just before that it reaches another neutron, and this pion is absorbed by this neutron and it becomes a proton. So finally at the time t, it is equal to r by c. A proton is converted into neutron and a neutron is converted into proton. This take place very fast. Okay, the time is a very short interval. The value is very short. This accounts for the exchange of particles without the variation of conservation of mass or energy. Now this is an exercise for you to do. Why this discovery of pions became so late? There are two reasons involved. You go through your textbook and write down the 2 points regarding the belated discovery of pions.